Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, it's a great pleasure to introduce Kim Hazelwood. Kim is an assistant professor at the University of Virginia, and she's been working on runtime adaptation and hardware integration. Kim got her PhD at at Harvard University in 2004, and she's been working with the PIN tool constructed at Intel, and she's been a major contributor to that. Kim's had a lot of awards, so I'll just name a few of them. She received the FEST Distinguished Young Investigator Award, an NSF Career Award, and a Woodrow Wilson Career Enhancement Fellowship, and finally the Anita Borg Early Career Award. So she's greatly distinguished, and we're very happy to have her. Today she's going to be talking about a dynamic adaptation for cross-layer integration.
Okay, so I'll just admit up front that I have a hidden agenda, and that's to brainwash the audience in some ways. So there are a few things that I think are important that I hope that you will also think are important by the end of the talk. So you can let me know how I did on that front. So what I'd like to talk about is why we need to start thinking about adapting our software while it's running and how it's going to solve a lot of problems, and why we need to start thinking about solving computing problems from more than just one layer in the system stack and having those layers work together. Okay. So first, let me start out by getting slightly nostalgic on you guys by letting you know about how I remember computing challenges back in the late 90s. Okay. So there, the main challenge that everybody was focusing on was performance, and that was pretty much it. And if you look at some of the graphs in the current textbooks, you see, I would actually say we did pretty well on that. Right? So in my lifetime, we've had a 10,000x performance improvement in our applications. So I would call that a raging success. Things were also nice and simple back in my recent history. So we had single core processor designs. So we didn't really have to worry about issues that arise when you have multiple processing elements that are executing simultaneously. So that was nice. These days, so I think I am somewhat preaching to the choir, because Ben gave a similar keynote where he commented on the fact that now performance is being trumped by some other issues that are becoming much more important. So some of those issues are power, temperature, reliability. So you can't give a power talk without showing a similar graph where we look at the power density over time and recognize that at some point in recent history, we surpassed the power density of a hot plate, and we were on trajectory to reach nuclear reactor status by a few years ago. So fortunately, we noticed this and changed some things, and we're able to dodge that bullet. And so that's why we have these data points over here. I think we were pretty good at solving that looming issue. We also have comments like that from the CEO of Google, where he said, at Google, we don't care so much about performance as much as power, because our data centers are using as much electricity as a city. You can't show a temperature. You can't give a temperature talk without showing the egg frying on the microprocessor. So a grad student realized he could cook his breakfast on his processor. And he did eat it, actually. It was pretty gross. And then actually, this is a fun demonstration of, who cares about performance or any of these other issues if your chip fries or the calculations that your machine performs are incorrect. So reliability is a big issue. Okay. So at the same time, we've had to start thinking about solving all of these new issues with another added constraint, in that we're no longer dealing with a single core Pentium 3 like we saw before. Now we've got multi-core chips, which are going to cause problems that will become apparent in a moment. Okay. So here's the quiz for the day. So my student came to me with some amazing results that you see on this graph here. So my student did this amazing optimization. And just to kind of give you your bearings, here are the Spec 2006 benchmarks. This is time, lower is better. And so the before case is the yellow, and the after case is blue. So my question to you is, what amazing optimization did my student do? Guesses?
Factor 2.
Yeah, factor 2 speed up. What did he do?
Bought a new computer.
Bought a new computer? That's a good guess. Nope, same computer.
Turned off the power save mode.
That's a good guess, but no.
Based on what the talk is. But
Yeah, good guess. Others? You all have to give one guess.
Cache? I don't know.
Did what to the cache? So I'll give you a hint. Same program, correctness it was still correct.
Okay.
Same inputs, same machine. Okay, I'll let you in on the secret. So the difference between the yellow bar and the blue bar is absolutely nothing was changed for the application itself. The difference is whether anything else was running on the machine at the same time. The fact that other applications were running on the other cores on that machine had up to a factor of 2 performance impact on the application that we're measuring here. Right? So why is that? Shared resources. So it turns out, you've got all these cores, but they are sharing resources with one another. So you've got things like here, 4-core chip from Intel, where the 2 neighboring cores share a level 2 cache. So you can see if you're running something next to your particular application that's using a lot of the cache, you're going to see significant performance degradations from that. Right? Not just that, there are a lot of shared resources. There's buses, there's access to the memory. All of this ends up being shared, and it has a huge impact. Okay, so then you could say, well, now I know that the 2 cores share a level 2 cache, so why don't I just factor that into my algorithms? Well, all of that is hidden underneath the ISA because this is the AMD Barcelona chip, also 4 cores, but this time all 4 cores share a level 2 cache. So it's not as simple as just trying to include all of this information into your algorithms. Okay. So what else is making our life a little more hectic now when we're trying to optimize? One of the things is heterogeneity. So there are a lot of forms of heterogeneity. There's some design heterogeneity where you have processors that might have a CPU and multiple GPU resources on the chip. So you have to figure out, how do I deal with this? How do I decide what goes where? So some of that is by design. Some of it is just sort of the microarchitectural differences that are hidden beneath the covers, like how much sharing there was between the level 2 cache that I showed you. Right? There's also heterogeneity that crops up because that just inherently crops up. You can't build the exact same processor twice. A speck of dust might hit one, right? What does Intel do with that? It hits part of the cache. Intel will turn off that part of the cache and sell it as a processor with lower cache capacity. So there's that. That's a known issue. And then there's this last issue that we happen to notice that I'm calling environmental heterogeneity. Okay, so let me show you sort of what we noticed here. So I had a student who was working on temperature analysis of applications. So he measured the temperature profile of the Perl benchmark and ran it once and showed me the results. And I said, you made sure this was repeatable, right? And that's when he ran it again and noticed this dramatic difference in temperature, 10 degrees Celsius difference between when he ran Perl on core 0 versus running it on core 5 in an 8-core machine. Okay, this is the exact same processor with, in theory, the same resources.
Was that because the actual chip had cooled between the two, or is that even at the same time the 2 cores are different temperatures?
Yeah, so some of it has to do with what the chip is, what that processor core is near. If it's closer to the fan, it's going to be running a little bit cooler than the others, right? If something hot is running next to it, suddenly that matters, right?
Where's the temperature being measured? Is it being measured on each core?
Good. Yeah. So there is a temperature sensor on every chip, on every core, but it's one sensor per core, right? And in theory, it would be in the same place, right? Whether it is or not, we can't really find it.
Extract this out from performance counters?
Yeah.
So those run the same dot?
What's that?
That's core 0 and core 5, so they run the same dot?
No, these are on. It's an 8-core machine, so there are two chips. Two chips in the machine. Yep.
Not surprising at all.
Yeah. So none of this is surprising in retrospect, right? Now, you guys, you have to admit, though, I saw some surprised looks on your face when I first showed this.
The same die at first.
Yeah.
That would have been surprising.
No, I mean, but there is some noise. So depending on whether if you run something twice, you're going to see it's going to be a little bit warmer than if you just ran it the first time when it was cold, right?
Turn on your machine, it's cold. So it starts.
Yeah, that's what I'm saying. So these are the kinds of things. Like if I were to ask my student to predict the temperature of Perl, right? That's
Does the temperature affect anything else significantly in terms of sort of? Can you see? Because I could see if you didn't know which die it was running on, you'd be very surprised if you ran it once and you ran it again.
And then it'd be much slower.
If there were some other impacts.
I mean, in this case, neither of these met the threshold to where some sort of thermal action would have stepped it. Like so if it starts to get too high, you can imagine what it'll do is it'll scale back its resources and start slowing the program down, right? So yeah, there can be impacts. There's certainly reliability effects at play here. This chip's not going to live as long as the other, right? So what's the bottom line? Why am I telling you all of this? What I'm hoping to get across is that this notion of trying to predict some sort of static running environment is not possible. You're not going to be able to do this. You really need to start thinking dynamically. You need to think about what is the current situation right now and how do I deal with that? Because I'm not going to be able to predict it, right? So we definitely need some dynamic techniques that can deal with the current situation. Okay? So what we're looking at are these types of dynamic and adaptive techniques to resolve some of the issues that I mentioned earlier. Okay? So let me tell you a little bit about some of the approaches that you might immediately come to your mind. So depending on who you are, whether you're a compiler person or an architect, you're going to immediately think about solving problems from your own camp, right? So if you're a compiler person, you say, I know how we could do this in the compiler. If you're an architect, you're going to have your ideas. But I'm going to tell you now that every single one of these layers has serious limitations. It has strengths, but it has serious limitations. Okay? So compilers have to be very conservative. You've got to ship one version of Microsoft Word. You're not going to ship a version that's running on Core 0 versus Core 5, right? Compiler, it's nice because it's got that global view of the program, but not so nice in that you have to make some sort of prediction, right? And I already showed you predictions, it's not happening, right? So OSs are getting much, much more complicated now. I mean, they're having a hard time keeping up with all of the heterogeneity and the multiple processing elements, and it's already getting very, very complicated to deal with these things in the OS. The architecture, okay, it understands the dynamic nature of a program, but it has this very limited window of knowledge about what's going on. So there's some restrictions there. And then you even have all the way down to the circuit level, where you have to be very conservative. You have to make sure that this thing works, right? So you have to handle every possible corner case and not necessarily the common case. Okay? So we're going to break all that down and say, why don't we just leverage all of the strengths of each layer and have them all kind of work together? Right? So that's what we want to do. And so you can think about, instead of just having this single interface between hardware and software, that we sort of spread that interface and are now allowing communication to occur between the operating system, between the hardware, between the running application. And we're sort of all going to collate all of this information in this virtualization layer. Okay? So this will allow us to do things like change the application in response to the current temperature that we happen to notice. Right? Or deal with reliability issues as they arise. Right? So, one question is, well, where does this virtualization layer lie? Is it above or below the OS? I think there are strengths to both locations. Right? One of the strengths of being above the OS is that you really have a good view of the application that's running. Right? So you can sort of separate that from the intertwining of all of the applications that are running and all of the kernel code. It's actually a little easier to operate above the OS. Right? But below the OS, you really see what's going on with the whole system. But you do lose some information about the specific software applications that are running. Right?
You want to optimize the OS too.
Yeah, so ideally you do. The problem is, by doing that, you lose sight of what the applications are. And you're never going to see a repetition of the interaction between one particular part of an application and the OS, again, right, you're going to see all sorts of different interleavings. It's just a much harder place to work. Definitely a better place to work. It's a much harder place to work.
When you say what's a much harder place to work, the OS?
Below the OS. Virtualizing below the OS.
That's sort of like the transmeta model, right? I mean, in some
Yeah,
sense,
so transmeta below the OS.
Yeah.
Some things that they can do. Yeah. The transmeta
It's the only one I can think of that actually did code transformations, right? I mean, because you have the VMMs or whatever, like, well, yeah.
Yeah, because it was doing translation, right? So it was going from x86
Right.
down
So
to this
yeah,
transmeta.
So it could have done arbitrary optimizations, code optimizations.
Right.
That's one of the few.
When you say virtualization, virtualizing what precisely?
Okay, so virtualizing this interface between sort of hardware and software. And what it really is just some place to take all of this information and do something about it. So that's what we're using it for. We're using it we can gather information about the applications that are running. We can send hints and things about, scheduling hints down to the OS, right? If you're above the OS, right? And you can actually transform the application. I mean, I'm going to tell you a little bit more about this layer and sort of how it works and what we're using. Okay. But the central idea is that you want to virtualize the hardware-software interface so that you can enable some communication between these layers and then transform your applications as a result.
So are you going to say more about what's in the virtualization?
Yeah.
I'm just confused about what happened to the OS.
Okay. So let me tell you about one way to do this, right? So you can virtualize above or below the OS, and so I'm going to talk about what you can do above the OS. Okay. So above the OS is process virtualization, so you're virtualizing the program that's running rather than the whole system, right? So there's process virtualization, system virtualization, and I'm going to talk about process virtualization. So here the idea is that you are taking a program binary, and as it's running, you're modifying it as it's going along and executing. Okay, so you've got the program binary. Instead of running that directly, you're transforming that binary, and you're running that transformed binary instead. Okay, it's slow to transform the binary, so you end up caching the results of your previous translations. Okay, so the system that we work on to do this is called PIN. Maybe most of you have heard of PIN. So yeah, we released it back in 2004. I've had 40,000 downloads, not necessarily different users, but we do distinguish by day, right? So if you download more than once a day, we don't count you. And then our PLDI paper from 2005 has over 600 citations at this point. So there are a lot of people using this for lots of reasons. Some reasons that we never intended. Once people realize that you can arbitrarily modify a program while it's running without any need for source code, there are a lot of cool things you could do with that. So you've got people doing security, you've got people just using it as a simulation driver, right? So you don't have to deal with the overhead of simple scaler, things like that. So that's what we're exploring for doing our virtualization. So what can we do at this level? What sort of things can we do? So let me give you a quick demo of PIN along with a quiz. Okay. So what I have here is my Visual Studio command prompt, and I have the Hello World application. So I print Hello World, hello, okay? So here's my question to you. Here's your quiz question. When I run Hello World, how many user-level instructions execute on my machine?
What's that? How many user level? An arbitrary number depending on what kind of thing you're running.
What you're running is Hello World.
I'd say 500,000.
500,000, okay. Is he crazy?
On your OS, anywhere between 100,000.
Okay, I'm on, what do you want to know? I'm on Windows XP.
It's got to be millions because you got to load in all the DLLs.
Oh yeah, I guess that's true.
To start up the process and do all the accounting.
Yeah, on Windows it'd be about 7 million instructions. If you engineer your OS properly, you can probably get it down to 100,000 instructions.
So you're saying somewhere between 100,000 and 7 million?
Yes.
Okay. That's a good range.
So let's hear the number.
Anybody gonna guess below that or above that?
Just read.
So
Okay.
above all,
Count that out.
So the truth is, like, so how are you going to answer this question? Well, the way to answer this question is you just run this application under PIN and tell it to tell you how many instructions.
Trick questions. You ask user mode instructions.
Right.
Yeah, expect the kernel
World
ones.
library probably. Yeah. Okay.
Yes. It's not like I'm asking an undergrad class. Like, you guys are experts.
Yeah,
you'd think you'd have a good notion of what's going on here, right? So here's what we're going to do.
Actually, we wouldn't. Nobody does. We're experts. We know we don't have a good idea what's going on.
Levels of abstraction. What's the answer to this question?
So here's what I'm doing. I am now going to run hello world under the control of pin, and I'm going to inject in the hello world a instruction count capability. So all this instruction count DLL does is inserts count ++ between every executing instruction. It's really just a few lines of C++ code, maybe 20 to do this. So this is what I had to write. And then, it's going to just work on any arbitrary executable. Okay. So I'm running it. It's going to print out hello world and now print out the count. So 367,000 user level instructions were executed. Interestingly, so the first time I generated this hello.exe, so I don't usually work on software development in Windows. So I went to Visual Studio. I said, give me a hello world program. There's like some, pulled down some menus, generated this thing. And at that point, it gave me this hello world program that it took like 5 seconds to run natively. It took, a long time to run it under pin. And it came back telling me there were like some billion instructions. And then we figured out, instead, if you compile it just at the command line using CL compiler, then
Get all that stuff.
Then we're down to 300. So interesting thing you learn. So you can actually use this to find bugs in compilers. That's a quick demo of the kinds of things that you can do if you are interested in just arbitrarily modifying your program. So I took the hello world program, modified it to inject count ++ in between everything, recognizing that count ++ needs a register. That register has to be stolen from the program, right? And all this just sort of works, right? So you have to reallocate the register. There's a lot that has to go on for that to work. Yeah, it does all that. I mean, it worked, right?
Yeah, I know.
And I promise you there wasn't a free register. This is x86, right? So it did have to steal that. So that's the system that we play around with for solving these types of problems. So then what do I actually do? Right? So now that you're buying into this whole runtime adaptation notion, the question is, what do I do?
If you stole a register, did that add some instructions?
Oh, yeah.
So the count, it's...
Oh, obviously we don't count those, right? The whole goal is transparency, right? So we have the original application to look at.
Okay.
And then we have a modified copy that we're creating on the fly. So if you're asking questions about the original application, we're going to pretend like pin's not running. So it's going to use the old addresses. It's going to use everything as if you weren't there.
The main program doesn't change its register allocation at all.
Right. The thing that's running does, but when you ask about it, it's going to lie and tell you what the original program would have done.
You don't know. You're not supposed to ever be able to see through. And so the things get tricky when you do things like exception.
Yeah.
You can't help but see through.
Oh yeah, especially on Windows. So, so what I end up doing spending a lot of my time doing are two main things. So now that we believe in runtime adaptation, hopefully do we believe in this now? Like you have to adapt your programs because we can't predict anything. And things like the environment are causing 2 to 3x slowdowns for us. Right? We can't pretend we're the only thing running anymore. So half of my work is on enabling this notion of runtime adaptation. And that's more the infrastructure of pin itself, getting it to work well. Getting it to work well. Getting it to work was easy. Getting it to work well was hard. Right? And then, once you have that system working, assuming you get the thing working and it works well, then what do you do with it? What are some of the things that you can modify about your programs? What problems can you solve? So that's the other half of my work. So let me start off by giving you an example of some of the things that had to be done to enable runtime adaptation. Some of the things that we've worked on to deal with pin. So that pretty much gets boiled down into two categories. We're either trying to get it to work on getting it to work on Windows, getting it to work on multi-threaded applications, right? Or we're trying to get it to work well, getting it to speed up. So half of our work is on improving performance, half of our work is on just supporting all the different platforms. Okay. So let me tell you about a few of the problems we've looked at in terms of improving the performance of the system. Okay. First thing you need to ask, what is the performance of the system? Right? Number one question everybody always asks about pin, what is pin's overhead for doing all that it does? Well, the truth is, it really depends on what you're running and the features of the program itself. Okay? So here's the Spec 2006 benchmarks run under the control of Pin compared to just running natively. Okay? So depending on the specific benchmark, the overhead is noise or almost 2x.
That's with what instrumentation?
Good question. This is with zero instrumentation. This is just Pin taking control of the system, maintaining control, translating the code so that it looks almost identical, caching that, and dealing with it.
So it doesn't grab any registers, for instance.
Right. It'll do it. Actually, one of our optimizations is we do sometimes reallocate registers if it makes more sense to have them, if the dynamic path could have had a better register allocation, we will reallocate the registers there.
What's the fundamental characteristic of a program that makes
it
the overhead?
Okay, great. So the main fundamental issues are, so there's this startup cost for looking at all the code and regenerating all that code. So if you regenerate all of that code and then the program ends, our overhead looks really bad. If you regenerate all that code and you run for 10 years, our overhead looks pretty good. Right? So we have this fixed overhead that depending on how long you're running the program, this is how much you can amortize it. That's one thing. The second thing is how long does it actually sit in that code? Okay. There are certain programs that like gzip. It's just one compression loop. Once you generate that code, you're done. Right? You just run it. But then there are things like GCC and Perl where you're going through different phases of compilation. So you generate all this code, you run it for a little while, you don't use that anymore, you move on to some other phase in the compiler. Right? So there we're not able to amortize our efforts as easily because we're moving through all these different phases. Right? So there are a lot of things. There are other things that are hard for us to deal with. Indirect branches are very hard for us to deal with. So if your program has more indirect branches, we're going to be slower than if it has fewer. Perl has a lot. Yeah. So if we could turn those switch statements into a series of if-then-else statements, you'd see a huge performance improvement. Self-modifying code. If your program modifies itself, we have to notice that because we have a generated cached copy that we need to now invalidate and regenerate.
Do none of these do that?
None. None of these do it.
Yeah.
Who does it? Windows, a bunch of Windows applications end up having self-modifying code. We notice this because we have to catch it.
I think you'll see if you look at newer versions of almost all the Windows code, it doesn't do that anymore.
No, well, I mean, I don't necessarily mean Microsoft Windows. I mean, so Adobe Acrobat
Yeah, that's what I mean.
has a bunch of self-modifying code.
I think
Games do.
So one of the things that's happened in the last few years is to avoid programs that jump into the heap.
Yeah.
They actually turned off execute in the heap,
Okay.
which means that, well, let's see. So to do self-modifying code, you really can't put it in the code segment because it's read-only. So you have to put it in the heap. But things like Adobe don't do that anymore because we turn off execute in the heap permission for like anything that plugs into IE.
Yeah.
And that's actually a general setting.
Games, though. So
Is it-
games
well,
are always
yeah,
doing stuff like
many
this.
games, but anyway, I think if you look at the newer versions, a lot of the stuff, it would do a lot less of that for the security issues. Yeah.
Right. But so yeah, those watching for it is very expensive, right? So there's an easy way to do it, which is every time you're about to execute code, make sure it hasn't changed. Of course, that's going to be very expensive. Right? So on some architectures, this is very easy. Like on the ARM, there you actually have to send a instruction that says, I've just done self-modifying code. So we just watch that. That makes it really easy. x86 doesn't have that. So the things that are hard, there are things that are hard for us to do. And the more of those things that your program has, the slower Pin's going to be on that program. Okay, so then there was the good question, which was, what is Pin doing here? And the answer was nothing. Turns out that most of the overhead doesn't come from Pin. It comes from what is the user trying to inject into the program. If they're trying to inject a lot of stuff into the program, of course it's going to slow the program down, right? That's their fault, right? So here's an example. Remember the count ++ example, the demo I just gave you. Here's the overhead of that. Right? So there, for these spec benchmarks, if you insert count ++ between your instructions, you're getting, in some cases, almost 8x overhead. Okay? So the biggest part of the overhead that people notice is the stuff that they've done, the stuff that they've inserted. Right? In theory, inserting a count plus plus between every instruction, there should be a 2x fixed overhead, right? Because now you've doubled. But because of all these other things and the overhead that we have anyway, that's where you're seeing this increase. So one of the things that we did for optimization, we do a lot of work to optimize pin itself, but we did do one cool thing to optimize or help hide the user's inserted overhead. So that's one of the things I want to talk about. And in order to understand that, you sort of need to understand where is time being spent when you run a native application versus a pinned application versus an instrumented application. Okay? So if you're running a native application, all the time is spent running that application. If you're running an application under the control of pin with no instrumentation, you're alternating between pin generating some code, and then you running that code, and then pin generating more code, and then you running that code, right? So all of runtime gets increased because you're going back into the VM to generate more code, right? Then if you add in some instrumentation, now you're alternating between pin generating code, running that code, running the new inserted code, generating more code, right? So this is where you're spending all of your time. So that's the normal way that pin executes, and then that's why you're seeing the overhead that you see. Right. So we have this mode called SuperPin, and what SuperPin does is it tries to hide all of that overhead using the parallelism available on the processor. So here's how this works. Normally, this is the native application running. Instead, now we just run pin in a real lightweight mode that every once in a while is going to fork off an instrumented slice of the application. Okay. So the instrumentation doesn't really happen in the main instance of the program. The instrumentation happens in a copy of the program. So both of these are running. So we have to do all these tricks so that if you do printf here, we don't want it to print twice. I've got 2 copies of this thing running. So we have to then do all of this stuff to stifle, figure out which system calls can we do twice, which one is it okay to do twice, which one do we stifle, what do we do about other things we don't know how to handle. Yeah. So, so we have all that figured out where we've gone through all of the system calls and figured out, okay, obviously we don't want to print twice, but, things like that. So, so this is actually a pretty hard problem because it's easy to say every 2 seconds spawn off a new slice. The question is, how do you tell this slice to stop? Right? And because you spawn it off before you've gotten to the point where it should stop. And it's only when you spawn off the next slice that you can tell this slice when to end. So now you can see this can be pretty hairy, right? And there's an added complication, which is you really want what you're doing with your instrumentation to be fairly independent. So like the count plus plus, this works well because you can just get a bunch of subcounts and then add them all up at the end. But if you're doing something that's very dependent, this isn't really for you.
So do you take advantage of the fork system call, or
yeah, that's what we use.
Because Windows doesn't really have a fork, as far as I know. Right?
Yeah, but there is an equivalent, right? I can't remember the name of it.
So it has something that does everything you need.
Yeah, yeah. We have to jump through a lot of hoops. So we have a whole paper on that, how we got pin to work on Windows, and you can see all of the details, the nitty-gritty details. Dealing with the fact that the system call IDs change every release of Windows.
So you're not tracking the instructions that are in the system calls, though, right?
Right. So we see that a system call happens, and then we let it happen, and then we're back. We basically have to catch the return from the system call so that we maintain control.
So for the copy, why do you even bother to call the system call when it was copied in the other one? Why not?
We don't. So that one we don't, right?
So you just basically get the result from the other run, and so it's just
And then each one everything we have to handle differently, right? But we don't hit print hello world twice or some mixed up version of hello world or something, or hello world out of order.
Why would it be differently if all you're doing is basically taking not calling the call but just taking the returned result as if it happened?
Yeah, I'm saying that example's easy, right? Because we just stifle it down here.
So which ones are hard?
So there's certain things like, so I guess malloc you don't want to do twice. There's the break system call, which you can do. There's a whole list of them that we kind of go through. Which ones are hard?
For malloc, you are going to need two regions in memory.
Yeah.
Okay.
So, and then break and maps and Yeah, all of this because we've got case statements of like, what's system call you're trying to do? Okay, no, I can do this. No, I can't. And a lot of it was just brainstorming. Can we do this twice? Can we not? How's that going to work?
So one of the problems I could see here is the it doesn't scale well with the number of system calls. So Windows has tons and tons, right? I mean, compared to Unix.
Because what we do is we end these slices either after 2 seconds or when we see a system call. Like we'll end one slice and then start the next slice afterwards. So in the ideal world, these slices are all the same size. But in practice, system calls are happening, sporadically, and so these slices are disconnected.
You have to deal with the sort of exotic things like the graphics device and things like that. I mean, there's all kinds of things that, for a general application would be pretty painful.
Yeah. So yeah, I mean, it's definitely not like it's an aspirin. It won't cure cancer, but it sure is good for a headache, right? So yeah, that's the way to think about that. And actually, it works pretty well. So if you take that instruction count pin tool, which had high overhead, that's something that's very parallelizable. Right. So here we had it was a 16-core machine, and we figured out, how much can we improve performance if we can throw a whole bunch of processors at it.
How many cores?
I think it was 16.
Oh, 16. Okay.
Yeah.
It's a hefty machine.
Right. Yeah. Otherwise, this would be. We sped up.
Yeah, so I'm curious. So do you have an idea of how scalable all that stuff was? I mean, it seems like as you add more cores, then you get more contention.
Yeah, I mean, it really, again, what it ends up depending on is the application that you're running. So an ideal application, which has no system calls, is going to scale perfectly.
Yeah, because they don't interact at all.
Right?
Well, even there, though, I mean, they're using the bus, et cetera. So at some level, it's kind of how well your 16 cores.
Yeah, and I already showed you, right, are they sharing resources?
Right.
The good thing about these things is that, yes, they're sharing resources, but this is a good thing because you have multiple threads doing the same thing. So so you've got like a prefetcher in your cache for you. Right. So that's just one example of one way to hide the overhead of what the user's doing. So that's one of our tricks for using parallelism to improve the performance of the system. And so one of the other things I can tell you about is one little issue with what happened when we changed Pin so that it now handles multi-threaded applications. Right? So when we first released Pin, it was just single-threaded applications. It was fine because you can do the spec benchmarks. But then when of course people asked for it, actually it was pretty straightforward, but there were some issues that cropped up, and I'll tell you about one of them. Okay, so mainly the issue that ended up cropping up with multi-threaded applications had to do with this code cache here. So remember, this is storing translated copies of code, right? And so the problem that crops up is this isn't a write-only cache, right? There's times we want to delete things, remove things from this cache, right? If we had self-modifying code, you need to remove things from the cache. If the user says, take out the instrumentation I had you insert before, you have to remove things. If you have you don't want to have this thing grow unbounded because it performs poorly if you do. So you want to set a size bound on this code cache. When you reach that size bound, you need to remove things. Right? A lot of reasons I need to take things out of the code cache. Okay. What becomes hard is how do you deal with this when you have multiple threads potentially running in the cache and you can't delete something out from underneath a thread? Okay. So here's how this works. At any given time, let's say you have 3 threads. And those threads are either running in the Pin VM or they're executing cached code here in the code cache, right? So let's say we get back into thread 1 gets back into the Pin VM and it says, hey, I just noticed some self-modifying code. I need to remove something from the code cache. It can't because it doesn't know where thread 2 or 3 are. And it can't delete something out from underneath these threads, right? So now it's kind of stuck. So we do have to deal with this though, right? We do have to support multi-threading and deletions from the code cache. Here's one option, and that is every thread gets its own code cache. Now Pin comes out, or this thread comes out and says, I need to delete something. Well, I know nobody's in my cache because I'm not there, so I can delete at will. So this is a bad idea, by the way. This is what Dynamo Rio did, and they found basically the same thing that we found. Question?
Why not just write a bunch of pointers so that it automatically, if it's in that code cache, it's just going to jump out to a part that you'll have a return address and you'll know exactly where it was.
So you're saying after every after it executes everything, jump out of the code cache into the VM.
So if you're in the VM and you realize that, well, there may be guys in this code cache, to free space in the code cache, you start by just writing pointers in there that jump to some place that's basically a recovery that says...
But you have no idea. I mean, this code cache is huge, and you have no idea where the threads are.
But it doesn't matter, does it? Because
you'd have to
jump with a
that's probably
address.
you could probably do that. I would guess that the performance is going to be really poor. To try and dig through the entire code cache and overwrite a bunch of things with jumps.
Stuff you're getting rid of. Right.
Yeah, no, but let's say you're in the middle of it, in the middle of that code.
Yeah.
Right? If there's a thread
it's like
stalled.
on-stack replacement, in some sense. You have to patch it correctly.
Right.
How big are these
And you
code
can't just
caches?
overwrite anything with an arbitrary branch, because a branch can be larger than certain instructions in x86. So you would be overwriting 2 instructions. And what happens if one thread was executing the previous instruction and now jumped into the second half of your new branch you just wrote? We've had this stuff happen.
Okay.
Right?
Actually,
It's definitely, there's no atomic write.
But you do know
branch
you do know what the old instructions were there, so you can...
Yeah, but you don't know if somebody's in that second half of what you're trying to overwrite. Let's say there were 2 instructions, and one and a half of those instructions are going to get overwritten by a branch.
Right. You can only overwrite things that are the same size as a branch.
Right.
Yeah.
Which means that you need to be jumping somewhere that's within 2 gigs. There's a bunch of restrictions there, right?
Sure.
Because you have to be able to write a 5-byte branch, but even there are instructions that are smaller than that.
So this actually has a direct application to non-virtualized systems. So Microsoft issues patches all the time.
Right.
Some of them are hot patches, which means that they have to actually do exactly the same thing to update code on the fly in the context of
running.
multiple processes and multiple threads running. So I think they have tricks, and I don't know how much.
Oh, so they actually patch while the program's running?
This. Oh yeah,
okay.
they call them hot patches, yeah. And they do this, and they don't have multiple copies for each thread.
Yeah.
There's only one copy. But I was curious, how big are these caches?
Yeah, so this is a good question.
Okay.
So this was Dynamo Rio said, yeah, we support multithreading, we have thread private code caches. And we scratched our head and said, that doesn't seem like a good idea. And that's when we generated this graph, which is, this is how much memory increases when you do this. So you get, maybe up to 6x the size of the original code cache. Because the problem is, a lot of these threads are doing the same thing. They've got the same code. So you've got 6 copies or 8 copies or some number of copies of the exact same code. So yeah, you've avoided that one issue of deletion at the expense of 6x memory overhead. This does not scale. You get, 100 threads. Yeah. So this was just for 8 threads. Okay? So this was not a good idea. So we never even played with that. Right? We knew we had to come up with a different solution. So we said, we're going to have a shared code cache across all the threads. We just got to figure out how it's going to work. Okay. So there's like a naive way to get this to work, and then there's a better way. And so I'll walk you through the naive way first. So one thing you can do is think about the fact, like, where are the threads at? The threads are either in the VM or they're in the code cache. And so at some point, thread 1 comes back into the VM and says, I need to flush something. So what it can do is say, I'm going to wait right here for everybody to come into the VM. And once everybody's in the VM, then I can flush. So it sits and waits. At some point in the future, thread 2 happens to come back into the VM and says, oh, you guys are waiting. OK, I'll wait with you. And then finally, thread 3 comes in. And only once thread 3's in, it says, oh, I'm last in. Let's flush the cache or whatever we need to do and move on to the new version of the cache. Here's the problem. You really never guarantee that thread 3 will ever come back. Thread 3 could be waiting on user input. And the user is waiting on something else to happen because there's code that's trying to run. And you're sort of stalled, right? So you're not able to generate any code. This doesn't work. So what we do instead is we partition the cache that we have up into generations. Okay? So what we do is thread 1 will come back in and say, oh, I need to flush the cache. But instead of waiting there, it says, I promise never to go into the old version of the cache. I'm going to start migrating into this new version. So it can make forward progress. Thread 2, at some point in the future, comes back into the VM and says, oh, yeah, I won't go back into the old cache either. So it moves into the new cache. And then whenever if and when thread 3 comes into the VM, then you can get rid of the old cache. So you basically just show that you migrate out of your generation and don't ever go back. Okay. So that actually is what we do today. That's what standard pin that's running multi-threaded applications. That's how it deals with deletions from the code cache. So we do have to have this high watermark in place so that we don't wait until we're out of memory to do this, because we need more memory. Right?
So if you're doing self-modifying code and you actually want to guarantee that every thread is running your new version of...
You really can never guarantee that, Yeah. So we basically guarantee that at some point in the future, they will eventually figure it out. What else are we going to do? Right? This thread definitely sees the self-modified code. The other threads are going to get there. So, hopefully you don't do self-modifying code and depend on all threads seeing it at the exact same time.
Yeah,
right?
It seems like just a disaster in terms of synchronizing, right? Unless you can guarantee the other threads aren't running.
Right. Yeah. So, that's just one of the crazy tricks we had to do, right? Or it was actually 2. So I showed you 2 tricks. One trick about just making pin work better in and of itself, and then one way of hiding the instrumentation that the user has. So one of the other things, that my students are particularly interested in, I can only convince them so much to hack on pin code. So mainly they just we just want to use pin and do something with it. And so that's what the second half of our work involves, is what do you do with the runtime adaptation? What are the kinds of things that you can now resolve now that you have this runtime sense of what's going on? So that I'm calling applying runtime adaptation. We've done a lot of things there. We've looked at things like all the way from dealing with reliability issues in the microprocessor itself to dealing with embedded systems, which we used to have a bunch of iPACs that we played with, but now we can use netbooks because they're kind of like constrained environments. They've only got a gig of RAM, right? Then, all the way up to things like dealing with parallelism. So there's all these people who are extracting parallelism from their applications. But we make the observation that sometimes you want to sort of rein that in. And that's if you have other things running on the system, you don't necessarily want to have the maximum number of threads from this application. You need to be a good sport. You need to get along with your neighbors, right? So the way that applications act in isolation is going to be very different than the way that they should act to be a good citizen. Just like people.
So, you're still doing this in the context of pin, right? So there's a trade-off because you're adding the overhead of pin to get the benefit. So can you really make cases for? So what's the sort of the final answer in some of these?
So it's a really good question, and the main thing is that at some point in the future, we're not going to have to make that argument anymore because there's going to be virtualization everywhere, and we're just going to leverage it, right? Now we do still, people are always going to ask us, what about the overhead of pin that you have to take into account, right? But there are already, you've got first of all, the Transmeta team is now at Intel, and they're doing similar stuff. So it's not too crazy to envision that there's going to be a virtualization layer on every future microprocessor. And if that's there, we'll just use it.
So that'd be below the OS, right?
Yeah. So some things will be, we'll have to adapt.
I see. Okay.
Right. So, yeah, we always have to fight that battle, which is like what? Don't necessarily think about. Here's one problem. Here's pin to solve that one problem. Think of it as there's a lot of problems that can all be solved if you have something like pin running all the time. Right? And then they don't all have to pay the penalty of here's pin versus not having pin.
Well, did you actually? The pin overheads were hundreds of percent typically.
No, it wasn't. No, let me go back to the graph.
Yeah, in the worst cases they were, more
But
than doubling.
worst case is not typical.
Well, but the worst case is the worst case, and people don't typically introduce things that slow down any programs for a factor of 2.
What about my netbook? How about this netbook? Do you think it's any faster? Do you think it's not slower than my machine?
You bought it, and you sort of made that choice.
That's what I'm saying. People are making that choice. People are choosing. It's not about performance anymore.
Use of a cache is more than twice
good enough revolution.
It just slows you down more.
It's a good enough revolution.
Not having a cache.
The thing that Jim is.
I don't see that as exactly analysis. I can't see anybody slipping in a layer of software which slows down any real program by a factor of 2 and getting away with it.
But no, I mean, I'm not saying pin's done. First of all, just because it's 200% for Perl now doesn't mean that that's what it's going to be like. So the next part of what we look at is, let's say that the overhead's free, for instance. What could we, I mean, is it even worth pursuing?
But, that's a fine thing to do, but I don't believe the overhead's going to be
That was
free.
the original argument for Dynamo, right? Was that it actually was better, it was faster to run on a virtual machine than to run native.
They got speed ups.
So
sometimes they
yeah,
get speed ups.
so one could argue, what are you doing that's taking all this time that Dynamo didn't do, or whatever?
We're running on x86 and not on P risk.
Okay.
Yeah.
Okay, that's the big difference. Okay, interesting.
Yeah. Nobody's ever been able to match Dynamo's performance on x86, and lots of people have tried.
So
what you don't want to use this for is optimizing your programs on the fly, because there you're always going to end up slowing the whole thing down. It's not worth it.
But if it slows things
But
down,
if it slows
things down,
if I can give you this,
have some sort of performance
if I can give
improvement
you
to compensate for it.
a lower power or a cheaper or a more reliable machine, would you be willing to pay 2x performance?
Depends what I needed out of the system. Sometimes it might be, depends what the power savings is.
I made that choice, right? I made the choice.
Do it all the time.
People
This is
are constantly choosing. They're not choosing performance. I had lots of options when I buy a computer, and I have never bought the very best, right? Because there are other things besides performance that are important to me.
Jim's point is just that.
It's the Prius argument.
No, wait.
Anybody here have a Prius?
No, wait.
You knew there was a Corvette out there.
Wait, when are
You didn't buy that.
So the question is, when you say 2x slowdown, are you talking about like a 2x slowdown all the time?
No, I mean, if I took Perl and I ran it for all day, the overhead would be noise. It would not be 2x.
Even with the indirect branches.
Yeah, because
I don't know if I buy that, because the Perl benchmark, the spec suite, it runs for a while. It doesn't just run and then stop.
Yeah, but if you run test inputs, the overhead looks a lot higher than if you run reference.
Oh, sure,
inputs.
yeah, but I'm assuming you're showing reference.
Yeah, I'm showing reference.
So let me ask you another question. So suppose we agree that 200% is too expensive.
Okay.
You seem to imply that there would be some way of not paying 200%. And I'm wondering what you're thinking. You're thinking there would be hardware support or something that would allow you to not pay the 200%?
Right, so half of my work is getting these things to work efficiently. So if I do my job there, then I don't ever have to justify 2x overhead because you're not going to see that.
So to put things in perspective, the VMs that people get, if you run a VM, you're talking about anywhere between 5 and 25% slowdown, but 5% is typical I think, for CPU-intensive stuff for virtualization. Right. So 200%, that's a big slowdown. And you could be arguing that the 200% is acceptable, but I was wondering, did you have techniques in mind that would allow you to get the 200%
down,
say 10% or something, or 10% over 110%?
Oh yeah, I mean, if I had that, I definitely would have presented that. Where we're at is we went from 100x overhead to 2x overhead.
And what do you think will get you from 2x lower?
If we could have some code generation support, right? So if I don't generate indirect branches, then I don't have to deal with indirect branches. And you don't have to generate indirect branches in a lot of cases.
So I'll make a case that trying to improve the performance of C code is actually a bad idea. I think the real big win here is JavaScript.
Okay, that's
so this is my that was my slide at the keynote. But the point is that JavaScript is incredibly
that's easy.
It's exactly the same thing. All the technology you're talking about in terms of virtualization is exactly the same problem that people building JavaScript for virtual machines have to deal with.
Yeah.
And they're rediscovering or doing exactly the same thing. I mean, and the advantage there is you don't have the starting point is not compiled optimized code. It's actually really slow. Yeah. So that's where the real opportunity I think is in this space. I mean, there's going to be a ton of JavaScript code. Already is. There will be a lot more.
You don't need pen for JavaScript because you have an interpreter engine.
No, but you need all the techniques in the virtualization layer.
But they're already there in the JavaScript interpreter, so they're rapid.
Yeah, so that's great. So I can just build upon that.
I think but I think that's I think one of your good stories here is all the stuff that you're doing here. If you move it into a JavaScript runtime, right? You wouldn't have to argue this argument about performance, right, which is irrelevant. And you can make the case that we can all these things with JavaScript code, which people right now don't assume they can do any of this stuff with it, and they're going to be running more and more of it. So, I mean, that's just my opinion, but I think
like don't get too hung up on I'm not trying to sell you pin. right? What I'm trying to sell you is the idea of having programs that adapt. What do you need to make that happen, and why would you want to do it? Right, so don't...
Okay, maybe you should go on to that part of the talk.
Okay, all right. So yeah, that's what this part is all about. Why would you want to do it? Here's some of the things that we've demonstrated you can do. Okay, so what I'm going to do is talk about sort of 1.5, right? Because 1 is pretty, you know, we've been working on it for years. 1 is brand new. So mainly I'm going to leave you with where we are now. Okay. So the first thing I'm going to talk about is something that you might not be all that familiar with, which is a reliability issue that arises when your processor is constantly fluctuating between doing lots of computation and stalling. Okay, so what you really want is a very smooth voltage pull, because that's what your power supply can deal with. That's what your power delivery system can't handle anything else. So it's a real problem. Here's where I get a lot of my ideas for what I should work on. The ITRS, International Technology Roadmap for Semiconductors, lists what are the grand challenges looking forward 5 to 10 years. And one of the grand challenges is this. What's going on here? I'll just tell you a little bit about it. So there's this well-known problem that you might have heard of called the DIDT problem. Okay. The DIDT problem has to do with the fact that you've got this power delivery system that needs to generate a constant stream of power to the chip in order for it to do its calculations. If it doesn't deliver enough power, the calculations don't propagate through the gates and you get wrong answers. This is bad. You send too much through and you're frying your chip. Okay? Both of these are bad, right? You don't want either dips or spikes in the stream of execution.
Those are your capacitors all over your board.
Exactly. So that's the way that people deal with it now is capacitors. They throw a bunch of capacitors at the problem. This is one solution. Unfortunately, that doesn't scale. And that's why it's listed as a grand challenge.
Doesn't scale to what?
To future processors and how much stability they need to be able to maintain. Because what it is, you can't exceed...
They're going to use less power.
Yeah, but basically the way that they're going to do that is they're going to lower the voltage. And when you lower the voltage, what you have to maintain is give or take 5% of the operating voltage. That's all that the system can tolerate. And when you lower the voltage, you also lower that what 5 to 10% means. So now we're to the point of, if you're at 1 volt, you can go up to 1.05, down to 0.95.
So
but that's dropping.
Isn't it going to just happen that they can't lower the voltage anymore? I mean, that's the story I heard, right?
Depends on who you talk to, right?
Okay.
Depends on who you talk to. But here's another reason this problem's getting worse. And that's because there are all these people proposing all these low power techniques for turning stuff off, turning stuff on. So now there's all of this crazy throttling happening, right? If something's not in use, turn it off. So it's the light switch problem, right? It's good to turn the lights off when you're not in the room. It's not good to turn the lights off every time you blink because you can cause reliability issues. If you sit there and flip a light switch, I promise you that it's going to burn out. So the same thing is happening within the microprocessors, and people are worrying about it. Mainly the circuits people are worrying about it, right? And because right now they just say, oh, throw a bunch of capacitors at the problem, then they realize that doesn't scale. So a couple other people are starting to jump on the bandwagon and figure out what can we do to solve this problem. So down here, we've got the hardware people. Let's add more capacitors. Right? Then there were some people up at the software level who were noticing that there are features of the code that cause this issue. If you have a lot of instructions executing in parallel and then you have a stall, that's that same thing. It's a spike followed by a dip. Right? Then what motivated our work was this microarchitectural proposal that came out of Princeton, where they said, why don't we have an on-chip sensor that notices these spikes and dips and an actuator that does something about it? So let me show you. So our work will end up falling between these two, between the compiler optimization level and these sensor actuator mechanisms. But here's the cool thing that ends up coming into play, which was that to motivate their work, they generated this code sequence. This is their power virus. Okay. Yeah, it's the power virus. So here's what it does.
Lots of divisions.
Yeah, it's one loop where you've got a bunch of dependencies in the first part. So all of these things are happening sequentially. And then you've got the second half, which everything happens in parallel. And this is in loop. So you see this burst of activity followed by stall, followed by burst, followed by stall. And if you size this just so, you start to cause problems. So this is what they use to, the Princeton guys use to motivate their architectural solution to the problem. And then one of the things I noticed is, here's a problem with their solution, is that their actuator is going to engage every single loop iteration. Right, so this isn't good. So I'm looking at the code. I can see what's wrong with this code. Why don't we fix the code? You know, people tried to fix the code just statically, but they had a hard time figuring out when this was going to be a problem. Like looking at the code and figuring out this is going to be a problem, that's hard. But having the hardware tell you, yes, I'm having a problem, that's easy. So that's what we do, is we take their sensor actuator extensions, and we say, great, keep those in place, but also let us know. Feed that information back up into the virtualization layer. And then that virtualization layer can regenerate that particular sequence of code. Okay? So, pretty straightforward solution. And what we found is like, so what do you do? What do you do to change the code to fix it? Turns out there were a lot of compiler optimizations. We came up with a list of compiler optimizations that might fix the problem, and they all worked. Because really what you need to do is just perturb that loop slightly, and then the problem goes away. Right? If you can take the high power section and the low power section and sort of weave them together, or even just sort of break up the high power section by inserting random instructions in between, you've cured the problem.
But that's sort of it's a contrived case, right? At some level, it's sort of like, it's like dealing with security. Here's an adversary. This is their adversarial attack, and you're going to come up with a strategy for dealing with that one attack. And the question, I guess, is how general is the solution, in the sense that how often is that attack like the real code, and how often can the solutions you apply to that one problem generalize to arbitrary problems?
Yeah, that's a great question. So really, there are two things that can cause these issues. One are the code-based problems, like a loop like the power virus. The other thing that could happen is an architectural issue where you have a stall, like an architectural stall, followed by, okay, now I've serviced that cache miss, and now I'm going to do a bunch of stuff.
Yeah, so that seems like that would happen all the time.
Yeah. So basically, we have some code-based techniques to deal with either case, right? So if you can figure out that there's this stall followed by a burst of activity, you can deal with the burst. You can either try and deal with the stall. Everyone wants to do that, right? That's a harder problem. But yeah, you can get rid of the stall, sure.
But isn't the
you can get rid of the burst.
Is to like stretch it out, which is sort of.
I mean, sometimes you can take the instructions that you have and sort of rearrange them, right? Okay. It's not that you necessarily have to spread them out. Okay. Right. So for this particular example, we took the power virus. What ended up happening is we took that power virus, and here's the before case where it was doing exactly what it was designed to do, which was this fluctuation. And then what we did was applied loop unrolling to that particular loop, sort of weave together the high power, low power sections, and that's where we were able to sort of slightly smooth out the problem here. So if you envision this, where you have some hardware mechanism to say, hey, I'm having a problem, software mechanism comes in and fixes the problem. That's really the best of all worlds. Okay. So then I'll just leave you with the last thing that we're working on. I have one slide for this, which is how do we deal with heterogeneity that we're starting to see in the microprocessors that are going to be coming out. So one of the things that we're starting to see is people are releasing chips that have CPU and then a bunch of GPU elements on it. And all these people are working on, okay, here's my program. How do I split it up between the CPU and GPU? They do this and they assume nothing else is running on the machine, and they're in a perfect world. So they're doing a good job at splitting things up, but they're ultimately making the wrong decisions. What they really need to be doing is factoring in the execution environment. So this is where we come in. We say, well, let's factor in things like contention for resources. If choosing between the CPU and GPU will change if the GPU is busy. Right? There are also things like the moving data from the CPU to the GPU is not free. They're not shared resources. You actually physically have to move the data over. So we're looking into things like data inertia. Where's the data now? Do we have to, should we favor either the CPU or GPU because the data is already there? How much does that cost? Of course, that should be factored in, right? So, basically what we're doing is taking some of the work that other people are doing and applying reality to it, which is that the execution environment is changing, and that changing execution environment should be factored in to your scheduling decisions. So that's kind of like a project we just started. A little bit of collaboration with the folks from NVIDIA and AMD on that.
It seems like one of these areas where the OS community sort of walked away from the problem, which is the GPU is a new resource, and typically, it would be scheduled like the CPU, but now you probably have two resources that you have to co-schedule.
Yeah.
And actually, the memory is another resource which the OS doesn't do a great job with, in terms of thinking about all three at the same time. Mm-hmm. But the other problem with the OS even doing this is that, like you're saying with sort of the data, it's like the OS doesn't necessarily know what computation is being done, or so it doesn't have that much information about how to make resource decisions. Right. And so it seems like it's a good opportunity. But one question you could ask is, why is it not the operating system making these choices instead of your layer?
Yeah, and then there it's more like, what are you calling the operating system? Maybe you would call what we're doing part of the operating system, right? If we're thinking about scheduling.
Traditionally, it would be very different because the operating system doesn't necessarily have all this information.
But we're already getting to the point where the operating system algorithms are getting so complicated and hairy because we're having to feed in very specific information about the underlying microarchitecture. Right? We already ran into that with recognizing that hyperthreading is different than completely separate cores. And two cores side by side that are sharing a level 2 cache are different than two cores diagonal that aren't. I mean, how do we deal with this? Do we keep making the scheduling algorithms more and more and more complicated?
The fundamental problem is that the hardware is more complicated. Mm-hmm. The operating system is this giant monolith that people really don't want to modify anyway. And if they try, and then now you got this other layer which has more information. But I don't know. I think that one strategy you have to think about is how you break up this kind of Gordian knot. I mean, it's all kinds of stuff happening. It's very hard to go in there and make changes.
Yeah.
And
what I think is so I think that the direction we're going, which is we're assuming that the OS is going to be able to handle all of this complexity, it's hard, and it's unnecessarily hard. So there are two approaches to making sure that your children are getting along. You either try to predict who their friends are going to be and only have them talk to them, or you break it up when they get into fights and they're not allowed to play anymore. That could be the approach to scheduling, is that you just sort of go with it, and when you see a problem, you deal with the problem. Right? Rather than trying to understand all of I didn't actually code in the difference between these two things. You just notice that hyperthreading is slower than separate cores.
Doing it at the application level is that the usage of the GPU goes across processes. And so if you want to actually allocate it, you need to be at the OS or the virtual machine layer to actually do that kind of allocation properly. Because otherwise,
and right now they're not. Right now people are just looking at, for my application, where should I run it? And they're not factoring in the other things that are running.
Right, but the OS.
That's why I'm saying I'm not picking a layer. I'm saying all of these layers are working together. The OS can say, look, you've got some serious contention there. Maybe you want to change what you're doing.
That's a whole separate problem, which is the question of how do you do resource allocation across abstraction values. And that one doesn't seem to be solved, either talking up or talking down across those layers.
Right, but so there's a notion of where are we today, and what are we moving in the right direction? Right.
But it does seem like if you move the GPU into the chip, basically, mm-hmm. So now you've got everything on the then you got to change the way they manage it. I mean, now the GPU.
What I'm saying is we already can't handle the slight heterogeneity we have today.
Right.
Try and throw in something totally different, like a GPU, which may not even have the same ISA.
So and so it seems like the OS needs new abstractions. I mean, but
that's why there's a lot of people looking at it. We're freaking out. What are we going to do about GPUs?
But the kind of thing is, a real instance of what you're talking about is this work that was presented at CGO with running user interaction type things and batch things on the same chip or the same.
Trying to
decide. Again, it's sort of like instead of saying we're going to solve the whole problem. It's just like when they start conflicting, we throttle essentially, and that's a little easier to do.
Right, that's what I say. Having something that's reactive is a lot easier thing to do than having something that's predictive. Right. So you need to be able to deal to make it reactive. Though it needs to be something that's done at runtime. Right. So it's easier and harder. So basically, just to conclude. My main point here is that you really do need to think about your applications adapting to the runtime environment, because the runtime environment can't be ignored. It was causing 2 to 3x performance differences, and we already know that these are important, right? 2 to 3x no good, right? So the fact that amazing optimization that my student performed had a 2x performance improvement, this should not be surprising to us, right? When we need to be able to deal with that. Right? So mainly, a lot of the work that we do is going to be leveraging lots of different layers and figuring out what is each layer good at. Hardware is very good at detecting problems, at noticing temperature. Software is terrible at that. It's inherently terrible at predicting temperature. But it doesn't need to because the hardware just can measure it. Right? And we just deal with it then. So software layers are really good at finding these really long-term solutions where you fix the code that's causing the problem. Or you get down to the root of the problem and resolve it, rather than constantly reacting to the same issue over and over again because you just have this limited window. Right? So if you think about things across the layers, that's when we get the best of all worlds. So let me just thank some of my collaborators at Princeton, Michigan, Virginia, Intel, Google, and AMD. And then all of my workhorse students who helped me generate the graphs and things like that for this work. And then also acknowledge some of the fun that we've had with this kind of work, where we got a little bit of press a couple years back for some of the implications that can come out if you have systems that are resolving issues on the fly. But none of this can compare to the day that we made Slashdot. And then we said we were done. We stopped paying attention after that. So
yeah. How much Twitter activity was there?
Really different from the other fields.
Yeah, track that.
That's pretty sad.
Yeah. So questions. You guys have been pretty good about asking questions.
Oh, yeah.
Questions, critiques, eggs.
What's the intellectual?
What's the contribution of my work? I'll take that offline.
The last 90 minutes, oh, wasn't so clear. Can you explain again quickly?
This is one particular PhD committee member who is known for doing this.
Would ask you, to understand, can you restate
the entire?
If you're gonna, that thesis you've been practicing for the last 6 months, you're gonna have suddenly a wonderful new insight that lets you explain it in 15 seconds.
Yeah, and at Harvard, there was that complication where sometimes you have people on your committee that you didn't choose, that the department chose for you, and it's always your worst nightmare.
Not me. I picked my worst nightmare for the committee.
So, hopefully I gave you guys some food for thought, right? Whether it's, this is a terrible idea and here's why. I'm fine with this. I can take it. But hopefully, you start to think about things in a more dynamic way and start thinking outside of your own little research area box. Right?
So what are you going to do next in this area?
So there's still a lot of work. So one of the things that I talked about at the end is really what we're working on, what we're starting now, which is how can we deal with the heterogeneity, CPU, GPU heterogeneity that we're starting to see. People are freaking out about it, and there's not a good solution yet, and we're still, trying to figure out how to navigate this area. So far, a lot of what we've encountered has little to do with the whole dynamic adaptation aspect and more about the logistics of how do you choose dynamically CPU or GPU when the ISAs are different, right? So you have to ship two versions of the code. Is that what we want to do, or do we want to abstract away some way so that you have something that gets generated into CPU code or GPU code?
Yeah, I was going to say, so you're thinking like in Pin of generating the GPU code on the fly?
Yeah, so that's an option.
Yeah.
Then, of course, we have to factor in the overhead of doing so.
Yeah, right, of course.
Right. But one nice thing about that, though, is that those GPUs they're changing all the time. There's all of these little parameters about how many processing elements, and they have to be grouped together where they access the same data, and then they all have to do branches at the same time. So this changes every single iteration. So trying to statically generate that code is pretty hard, and that code's not going to work well for the next version of the processor.
But don't drivers today generate code dynamically?
Yes.
Right, but wouldn't it be nice, though, for the programmer to have some input there about some of the higher level notions of actually this part of the program is more amenable to that than these other portions, right? So the code generators that are actually the drivers aren't perfect, right? Sometimes they generate some pretty poor code just because of the way that they work, right? And because you can't give them the hints that you need to give them, right? So how should this work? Do we need an end-to-end solution to this problem? So I think that's where we'll be spending the near future. A lot of the applications that we look at, though, are really driven by the students and what their interests are. I've learned I can't force them to be interested in something just because I am. So they kind of drive that part of it.
Are there benchmarks? I mean, it seems like the spec benchmarks wouldn't be very amenable to GPU stuff.
Yeah, so at UVA, Kevin Skadron's group has generated the Rodinia benchmark suite.
Really? I've never heard of that.
Yeah, and so it's a collection of, he didn't create these benchmarks, it's more of a collection of existing utilities that have little GPU-style kernels. So this is what a lot of people are using, but yeah, it's a good question, and it's the first question we dealt with, which was, what do we run?
Yeah, you have to evaluate it.
And at some point, someone figured out that there really isn't anything, and somebody needs to create the new spec for GPU, CPU, heterogeneity.
So have you thought, one of the interesting questions is, and Jim made this point years ago with singularity, people want their computers to be predictable in some fashion. So have you thought about the opposite problem, which is given the adaptability, how you would actually control this from an OS and make things predictable? So you could be adaptable, but see, the downside of being adaptable is you're variable.
Yeah.
And that can be bad. So getting the best performance instantaneously is great, but sometimes people want more predictable behavior, like please don't run my battery down, or...
Well, but you can make that be your criterion, right? I mean,
Right.
we have this
But I'm just wondering, have you thought...
Yeah, I mean, that's interesting.
The OS side, there's an OS side to this thing, which is how would one let the user control the adaptability? Is that even a good idea?
Right. Yeah, we're definitely going to have some bounds on it. And in some ways, when you have... So this is the argument of performance, wall clock performance versus sort of responsiveness of the system. Right? There you don't really care how much slower it is as long as when I move my mouse, the actual mouse moves on the screen. But if I'm sitting there, I don't really care if things are variable until it matters, right? So, so that's a hard problem, but I think it's really going to boil down to the specific application and how much responsiveness the user is going to expect, right? Of course, we're going to have some bounds on what we do. Try to do things when you're idle.
You obviously have done work on a number of, and this will be my last question.
That's okay.
But you obviously done work on a number of areas. I'm wondering if you had gathered any insights about, what might one do in an OS to control this stuff or to make things more predictable?
The easy things that they could do, that the OS could do, is this is something that's kind of like your spy sweeper, which runs when your system's idle, right? So it kind of collates a lot of the information that it's gathered while the program was running and sort of decouples the gathering information from the doing something about it, right? We don't necessarily want to do that for something like reliability, right? That needs to happen. There we have to focus on just making it as efficient as possible so that there's no lack of responsiveness, right? But yeah, the more complicated things we could potentially do in the windows of opportunity that we have when the system's idle. Yeah, but yeah, it's a good thing to think about.
Okay, so let's thank him.